All right, we'll go ahead and get started. Are you guys able to hear me? All right, awesome. Well, thanks for joining my session. Hope you all had a good lunch. And my talk today is about next generation storage architecture for scale-out block storage. I'm focusing on scale-out block, but I think a lot of the thoughts I'm presenting here, I think apply to storage in general. My name is Jaspal Kohli. I run the storage team at Fungible. Been there about 6 years now, really joined at a time when we were starting to think about the DPU, right, the data processor we have built, and really focus on hardware-software co-design on what kind of processor would work really well for storage data path coming up. So in my talk today, I'm going to have three main sections. Start with motivation, right, why we went down this path. Then we identified some key architecture principles that I think emerged from our thinking and our implementation. I'll give you an overview of the Fungible Storage Cluster, which is an implementation of this architecture, and then finish up with a summary. So in terms of motivation, it's always really important to think about why we do something before we go down some path of endeavor. And quite often we find that in our industry, technology shift motivates you to change the way you're thinking about implementing something. And then quite often there's a change in workload patterns, a change in the way amount of data that's being generated. In this case, I think really there's a perfect storm of both of these things changing rapidly over the last 5 to 10 years. And if you think about the technology shift, in the 90s, 2000s, we got used to CPU ramping up using Moore's law, right? We're seeing a great ramp up in general purpose compute. That has flattened out, and in its place, we see rapid growth in flash storage. We see rapid growth in networking, already at 100 gig and moving north of there. And then at the same time, I think there's a trend to use specialized compute. So I think GPUs have proven that you can specialize your architecture and really do well at certain implementations. And now DPUs are playing that same role for much of the data-centric workload. Now, at the same time, the workloads have been shifting, I think because of the popularity of the public clouds. A lot of the workloads have gotten broken down into microservices. Instead of one application using storage in one way, an application is broken down into many pieces, and each of these pieces need to use storage in a slightly different way. Some use requires data protection, others may not require data protection. Some require much higher IOPS than others. Latency versus bandwidth, these are all sort of different considerations. So I think combination of these two things is really driving towards a new architecture which is at the right start workload centric. So I should be able to say, hey, I need this amount of storage with these characteristics, and many of these different things should be able to coexist in the same storage. Now, while flash and 100 gig networking is certainly changing the landscape, cost still remains an interesting consideration, right? Flash is expensive. So you want a storage system that not only provides you all this power of the new technology, but does it at an efficient cost, both in terms of how much flash you need to deploy, and then the operational costs associated with it. And obviously, we want to be able to scale because the workload is growing, right? Over time, we have more and more workload. And then we want to secure all of this storage because so many different workloads are sharing a common footprint. So let's take a closer look at each of these trends, right? So when I think about technology shift, right, we got used to an environment for building storage stacks where the compute was much more powerful than the devices and the network. So our tendency was to add algorithmic complexity in the stack to compensate for the lack of performance in the storage itself or lack of performance in the network itself, right? So we had to resort to techniques like caching, doing metadata lookups right in the client. We had the flexibility of mapping from block to intermediate representations like objects, and then mapping back from object to file to block. So you're going through several layers of abstraction changes from the path from an application doing a read or a write to when it actually hits the media. And we had the luxury of 100 microseconds to even milliseconds of additional latency added in that stack, right? And the other, I think, interesting aspect was that we had to resort to things like striping and hashing to fully utilize I/O devices in the network. So if a single application needed more performance than what a single device can provide, then the stack fundamentally had to find some ways of assembling multiples of these for a single application. Now, moving forward, a lot of this has completely flipped on its head. So a single SSD can actually serve now many, many applications, right? So that need to stripe necessarily and hash is not necessarily there. On the other hand, the latency characteristics are such that the storage data path really should be executing in microseconds, single-digit microseconds, not hundreds of microseconds or milliseconds. So I think we are going towards a world where thin clients are important, and they are not mapping through many layers of abstraction. They are directly speaking a protocol like NVMe TCP. And then the storage target stack is also designed to be extremely efficient, including how the data protection scheme is implemented. And then for cost reasons, we need data reduction to be done inline. So things like compression, erasure coding, deduplication, all of this has to be done inline. Now, similarly, if you look at sort of the workload side of things, we started building storage systems that really met specific applications. So sub-applications really benefit from storage being directly attached to the processor. Then we had JBOFs, which said, hey, I need more than one SSD. And then we had sort of all-flash arrays, which said, hey, sometimes an SSD can fail, so I need data protection. And then, of course, scale-out has also emerged out of that. Now, while each of these schemes was optimized for its own use case, we ended up with silos where the utilization was poor and we had higher cost of maintenance, right? And I think what we want to go towards a world is where we have a unified storage pool that can provide you high performance and low latency, and can do it with configurable volume properties. So in NVMe terms, each namespace should have its own set of properties. What type of data protection I need, what encryption key I want to use, whether I want compression, dedupe, right? Even block size, what's my optimal block size? So all of these are configurable. And the other thing is that the growth of this always-on data is also immense. So we're not talking about small amounts of data that you efficiently store and access. The amount of data you need to efficiently access is just growing leaps and bounds due to AI/ML type of workloads. Sorry about that. Okay, so one thing that really comes to mind is, in our industry, I think we tend to recycle ideas a lot, right? I mean, there are things that happen and we adapt to that, and then things change and we adapt to that. So an analogy that comes to mind really is what happened with networking, with the internet boom. So similar to storage, network packet processing used to run on general purpose compute. And with the internet boom, I think people realized that you really need a specialized processor for packet processing. And really the data path of packet switching really needs to move to specialized processors. And as a result of that, you really need to pull out the control and management plane into its own entity, which is then has its own areas of specialization. So in the networking terms, we had these route tables that get downloaded into these ASICs that do actually the packet processing. And these ASICs are able to do that at very high speed and also apply inline functions for security, for inspection, for network address translation. And then that played out even more when network virtualization came in public cloud. So when you needed to virtualize the network, not only were you doing this routing, you were also doing it for VMs, creating network overlays. And I see a very strong analogy here, what it is, packets per second is really now IOPS for us in the storage world, right? When somebody does a read or write, fundamentally it's not that different from routing a packet from source to target. And then, what we are calling NVMe namespaces are really kind of analogous to network overlays. So I think the first thing we need to do is to really do that clean separation of these three roles in storage. So the data path really, what it needs to do is streamline that access from storage clients to media. Obviously, it has to terminate protocols, provide functions like quality of service, has to do block mapping for sure. because not every block can be directly placed in some convenient place. It needs to do thin provisioning, again for cost reasons. But other than that, really, everything else can be moved out into the management and control plane. And by management, really, the functions are really how do I manage the cluster? What does my volume configuration look like? How do I enforce multi-tenancy safely? And the control plane actually becomes even more interesting because now where you place data in the network is largely determined by the control plane and not the data plane. Of course, the very granular block level mapping probably still done by the data plane, but the control plane can play a very strong role in actually figuring out where in the cluster data belongs. And then even quality of service provisioning is something for the control plane to do. And lastly, but probably most importantly, just like in network, when a link fails, new routing tables have to be created. Here, if an SSD fails or a storage processor fails, we have to reroute requests to that data, right? And so this is a place where the control plane can really take over. So the next sort of thing to look at is, okay, how do we make the storage data path really high performance and flexible at the same time? And really our thinking here has been that instead of thinking of the storage data path as one entity, it's really a composable pipeline of stages, right? So you can think each stage of your storage data path as a modular piece in the pipeline, right? So for example, when a request comes in, you go through obviously the protocol part, you might apply some inline functions like compression, encryption. Then of course you have to map it to a specific area to store in, and then you may erasure code it, for example, or replicate it. And then finally you get to space allocation. Now, each of these can, if it was a stage in the pipeline that can be composed by the control plane, then you really get to a model where you have both high performance and the flexibility you need, and the agility to do that, come up with new schemes. And of course, clustering and scale out is a very important aspect, right? You really need multiple of these data path processors that I'm calling here to cooperate in providing a single namespace. So you end up with kind of three interesting pipelines. You have requests coming from the pipeline or from the client that will go through your pipeline and would go out to another data path processor in the network. You have sort of the converse of that, where a remote data path processor is sending you a request to store, some portion. And then, of course, you may have some things that goes direct from a client request down to a media attached to the data path processor. So each of these pipelines, if it can be constructed by the data control plane, then you end up with a structure that's extremely flexible. Now, one example of this is implementing data protection directly across the network. So in, I think, previous implementations, what we have seen is that today we are only replicating data across the network. So local data protection, like parity schemes, is done within a processor with attached media to it. But anytime you want protection across the network, we are resorting to replication. And there's really no reason to do that. We can erasure code directly across the network with a combination of the control plane and the data plane. And you can see the benefit in all respects, right? First, space overhead decreases dramatically. Instead of, if you do three-way replication, you have 200% space overhead, right? You're down with 16+2 erasure coding. And I'm assuming everybody understands this, the EC terminology. So it's just talking about Reed-Solomon, where you have 16 data stripes and 2 parity, and it's totally flexible. So that reduces the space overhead. Not only that, the write amplification is reduced by the same factor, right? So for 4 kilobyte write that the client did, I'm not writing 12 kilobytes. I'm writing a much smaller fraction of that. The other thing is, because of the property of Reed-Solomon, the M plus N is very flexible. So if you really wanted to say, hey, my application is super critical, I need 3 concurrent failures in my network to be protected against. So instead of replicating 4 times, you can simply go to erasure coding 16+3, all right, which would give you instantly that protection. So here in the graphic, what I'm really showing is that the control plane is essentially dictating where, if you had like a 4+2 EC volume, the control plane dictates where pieces of these volumes are spread in the network, right? And I'll kind of go into the next level detail in the next chart. And then the second aspect, of course, is redundant paths, right? If a data path processor were to fail, you need redundant paths where the client should then be able to use an alternate path. Now, NVMe has the ANA scheme prescribed. And if you implement it this way, the interesting thing is the number of independent paths you have and the number of media redundancy is actually independent. So even with a 4+2 scheme, I could have 3 data path processors that are capable of serving this data out of the network. Right? In replicated schemes, there's a one-to-one relationship. Only if a processor has the full complement of data stored locally can it act as a data path processor. When the data is spread out in the network like this, any processor in the network can actually act as the data path processor. Of course, with the proviso that any state that you have, any temporary state that you have for the namespace, for example, uncommitted transactions, right, that could be sitting in a device like NVDIMM, of course, have to be sent to those processors or made available over the network. Okay, so moving along, let me come back to this notion of the control plane really determining, where data lives. So fundamentally, I think when we are looking at scale-out storage, there is a notion of a fault zone, right? And the fault zone is the set of devices, the set of media that have correlated failure. So these could be equipment that's sitting in a rack, and the rack power fails. It could be as big as a room, right? Where you say, hey, this room could go out due to a fire or whatever, something like that. So once the control plane knows what the fault zone is, it is able to then granularly go and place elements of each volume inside that fault zone. And you can have schemes all the way to the left where essentially you're only providing a raw volume, not unprotected, very much like a DAS replacement, right? But even there, you might want anti-affinity. So if I have an application that's doing 3-way replication in the application, I certainly don't want that my 3 raw volumes are in the same fault zone. So the control plane can certainly help in that regard. And then, all the way to any EC scheme you can imagine, or even 3-way replication, if that's of interest for some reason, that can be determined by the control plane. Similarly, the control plane has a really good idea of what the capacity available in the cluster and also where IOPS are available. So when you think about the path going from the client all the way to the media, there can be number of bottlenecks along the way, right? The network could become a bottleneck, right? The data path processor could become a bottleneck, or the media could become a bottleneck. So when you say this NVMe namespace must get a million IOPS, then you better make sure that all those paths in the network are provisioned, right? So this namespace can reliably get a million IOPS. So I think that's really an advantage of this notion of controlled data placement. The other interesting thing is that, the flash technology is moving so fast, right? We are getting larger SSDs every day. We have media types like SLC, QLC, TLC, more to come, right? By having the control plane decide placement, you can actually match device size and property to what you want for your namespace, right? And you don't have to have even-sized devices. You can replace them over time. And even more interestingly, I think with super large SSDs, right, you can actually have partial faults. So you may say, hey, some NAND chips failed, so part of my SSD is gone. It doesn't mean that I need to fail the entire 128 terabyte or whatever size SSD I created. So I think super important aspect of the architecture. The other thing I wanted to touch on is what happens when the cluster changes shape. And change could happen with one of 2 reasons. Media failure causes you to rebuild, and then you may add or remove elements from the cluster. So, in this model, really, we can start imagining rebuild as not an activity that involves rebuilding an SSD. It's really about rebuilding each namespace that is sharing that SSD. Right? And that has 2 really remarkable kind of outcomes. One is the number of elements that are involved in doing this reconstruction. scales with the number of volumes that share the SSD. And the number of devices that participate in the rebuild activity also scales, right? So in this example, I'm showing 3 volumes, right? A, B, and C. They all have one piece of this media element on the left, right? When that media element fails, each of those 3 volumes are getting rebuilt, but where they find space are all in different media elements. Which processors do that work are really the primary data path processor for that namespace. So this whole activity really scales more and more as clusters increase, as media sizes increase. And then similarly, actually when you resize your cluster, one of the issues with hash-based distribution is that you do have to rehash, right? And no matter what you do with consistent hash or other things, you will always have to move a certain amount of data. When the placement is managed by the control plane, really what you have is a placement graph for each namespace. So you don't really need to move anything at all in the best case scenario, right? Because every existing namespace knows its graph in the network. And the only time you need to start moving is if you really start to create empty spaces in existing nodes. And that again is orchestrated by the control plane. It's not something that the data plane has to wake up and say, oh, my cluster size changed, I better start shuffling data around. Okay, and then the last topic I wanted to hit on in terms of architecture is this notion of linear scaling. Can a scale-out storage implementation truly achieve a linear scale? And I think we've all struggled with that, where we think, hey, it should be possible, but then you actually build your implementation, and then you find that, hey, certain algorithms did not scale, or my network interaction went super linear, and as I grow the number of nodes, I'm not getting linear scaling. So in this architecture, I think one of the things we really tried to focus on is that the work done by a data path processor remains fixed, independent of cluster size. And as I was showing in the earlier graphic, a data path processor only has a few pipelines that it implements. And as long as those are the assigned pipelines to it, its role doesn't change in the cluster at all. The data path processors are not keeping track of each other. There's nothing in the data plane which says, oh, I have 15 other guys to work with. Those instructions are coming from the control plane on a per namespace basis, which says, hey, when you get a request for this particular volume, you have to distribute to these other 6 guys or 10 guys, right? And that's a map that's described by the control plane on a per namespace basis. So really, when you put all of this together, I do believe we can achieve linear scaling as we increase the number of DPPs. And furthermore, the speed of recovery, right, when you look at rebuild or data path failover, that actually is better than linear, because as you increase the cluster size, your rebuild speed actually gets faster and faster. And if you think about a data path processor failing over, right, that path now is taken up by a larger number of DPPs in the clusters. So the work done by each surviving DPP gets lesser and lesser as you scale up the cluster size. So I think both of these properties do scale very well. So now let me switch gears and talk about our implementation of the Fungible Storage Cluster. And really, again, the theme here is architecture specialization. So I'll start with an overview slide, and then I have a couple slides that go deeper into the control plane and the data plane. So the Fungible Storage Cluster really consists of 2 main entities. There's an FS1600 storage node. It has 2 fungible DPUs and 24 NVMe SSDs. There is no other processor in the FS1600 node. The entire storage data path is implemented in the fungible F1 DPU. I'll talk a little bit more about that. And then, of course, all the control and data management functions are pulled out into a software entity that can run on general purpose hardware with a generic NIC and, of course, local storage to maintain the state. We do have another entity which is optional, which is a storage initiator card that can be attached in the host. And basically, this offloads TCP processing, virtualization, a bunch of other functions in the data path right on the client side. We do have another talk on Wednesday. I'll point you guys at the end on that piece itself. So, it's a full feature implementation. We have essentially adaptive storage on a per volume basis. You can specify on a per namespace all these different properties. There is full implementation of block CRC on a per block basis. So, the data is well protected in terms of integrity. And because of the redundancy in the storage, we can actually repair CRC also, right? It's not just a detection mechanism. So if you do detect bad CRC, you're able to reach out to redundant pieces and correct it. Of course, we have snapshots and clones. And then the Composer node exposes not just a GUI, but an intent-based API, northbound. And we do have Cinder and CSI plugins to connect into orchestration systems or, any custom orchestration system that somebody may have. So let's take a closer look at the control plane and then at the data plane. So the control plane can actually leverage a lot from looking at modern distributed systems. So it really benefits from being implemented using microservices on a framework that provides distributed services like a scale-out database, a message bus, an API gateway. So if you're used to modern cloud applications, right, started with public clouds, but now sort of coming back on-prem as well, this is a very familiar domain, a lot of technology available here. We don't need to, kind of reinvent the wheel here. So really the Fungible Composer is a set of microservices built on this kind of platform. And clearly storage is at the heart of the service, but there are other services there also, telemetry, topology, logging, and how to upgrade the cluster and things like that. And all of this software is implemented in high-level languages, primarily in Go and Python. And so, this is an area where, unlike the data plane, you're not concerned so much about cycles, cycle counts, and things like that. You're concerned about agility. You're concerned about how to scale that independent of the data plane. Now, the data plane, on the other hand, is kind of the opposite problem, right? You really are concerned about counting exact number of cycles that you spend taking a request and fulfilling it, whether it be a read or write. So this is where I think we have gone through an extensive hardware-software co-design of the Fungible DPU. Again, we do have a talk that Jay will be giving on Wednesday about why Fungible DPU is a gate processor for storage. But I will highlight a few things here. So one thing is that, of course, all DPUs have programmable cores. They have accelerators that help you do functions like compression, encryption. But if you look at this notion of these pipelines, right? If you were to imagine that each namespace is a pipeline of these stages, right? What you need is a processor that's capable of scheduling these pipelines and switching them between them at very rapid rates, right? Measured in nanoseconds, right? Really, we are down to that level now. So this is where I think the DPU design comes into play. I think we believe we have designed a processor that's really capable of doing that. The other thing is that your access to the network and to PCIe. I think this is a place where we spend a lot of cycles, dealing with interrupts, dealing with long latencies. So this is another area where the DPU is highly specialized on how the software interacts with the network and how does it interact with the PCIe bus. And then finally, I think the memory model is super important, right? Storage is a very stateful application. So the amount of memory state you need in the data path processor is super critical. And it comes in several forms, right? There's a form of memory usage where it's really for payload. And payload, for the most part, is streaming through the processor. It's coming, it's going through certain manipulations, finally reaching the media. Very little to do with your programmable cores, right? And then you, of course, have the metadata, which is all about how efficiently can the programmable cores manipulate this metadata. So again, a lot of specialization in this area. And we do have a secure enclave as well. I think, of course, a large element of security is protecting the data. But we do need to secure the processor itself to make sure that bad software cannot get into this kind of processor. So, I will not get into sort of the exact performance numbers. Jay will share that in much more detail in his talk, but we are able to push, 6 to 7 million IOPS through a single DPU, very high bandwidth, especially if you use larger block sizes. The path length through the DPU is really measured less than 10 microseconds, typically in the 5 to 7 microsecond range, and this includes many inline functions, right? This is not just about implementing read-write, but is really taking it through compression, encryption, erasure coding, other functions, calculating block CRC. And on the linear scaling front, we have measured linear scaling with those numbers, right, up to 32 DPUs so far, so 16 of those FS nodes. We are in the process of qualifying sort of the next multiples. So far, we have not seen any issue where we see, hey, the work of a DPU when it was a 4-node cluster versus a 16-node cluster change in any way. So we do believe that we should continue to see this linear scaling. Okay, that pretty much completes the material I wanted to cover. So to summarize, right, I think the reason to think about a new architecture is really this perfect storm because of big technology shift in our industry, coupled with really the workloads changing from single applications to this cloud-like model. And some of the core architecture principles we've had to develop, I didn't shift the slide. The core architecture principles we have had to develop, first of all, clean separation between the control plane, data plane, and the management plane. And to really think about the data path as not a single implementation, but really as a composable pipeline that can be granularly controlled by the control plane. And then the data protection, I think, needs to flatten across the network. I don't think we can afford this hierarchy where you're doing local data protection and then replicating data across the network. I don't think there's any reason to do that because networking has become powerful enough to support that. And if you have a computing element that's powerful enough to erasure code inline and distribute the data, there's really no reason for us to pay that penalty anymore. I think the controlled data placement is a key aspect of this. Of course, we derive the luxury of linear scaling out of all this. And then, we have demonstrated with the Fungible Storage Cluster that indeed the Fungible DPU, is the right data path processor to implement this new architecture. And then on the control plane side, I think we can enjoy leveraging distributed systems technology that the whole industry has developed really to make the job of the control plane much more agile and scalable. Right? So that concludes my talk. I do want to point out a couple related talks. So Jay will be talking about the rise of DPU-based storage systems and really take you through details of why the DPU is great as a storage processor. And then my colleague Pratapa will talk about how the DPU can also be leveraged as not only on the target side, but as a storage initiator. All right, thanks. Thanks for listening to my talk. I'll open up to questions. I think we have about 15 minutes or so. Go ahead. In the black shirt. Right. No, so that really measures, like, for example, right, if you were to run FIO in your host and you had a single DPU serving that IO, how many IOPS you could get total, right? Actually, one client is probably not enough to drive that, so you would have several load generators talking to one DPU. So that's the total throughput that you could get from a single DPU.
More of the DPU's capacity of processing power rather than if you have SSDs connected to that, you can solve those
Correct. Sorry, I should have repeated the question. The question was that the number I showed there of 6.5 million IOPS is really the DPU's capacity to process those IOPS. And yes, the answer is yes. That assumes two things. You have the complement of SSDs required to generate those IOPS, and you have a network powerful enough, right, to support that. Yeah. No, so if you look back sort of at this picture, right, so the DPU is sitting inside this chassis, and so it's the only processor, right? So on one side, it's connected to the network. On the other side, it's connected to SSDs. So it's the only thing that's really providing the competition.
What's the typical capacity of a DPU in terms of storage?
So, the fungible F1 DPU has 64 lanes, so you could connect up to 16 SSDs. In this topology, we have connected 12 to each DPU. Right?
Sorry, 64 lanes, and you're connecting, how are you connecting 24?
So there's two DPUs inside there. So each DPU is connected to 12 SSDs using 48 lanes. Right?
So each SSD.
It's Gen 3x4 in this generation of technology. Of course, the PCI generations are also going forward.
So a given DPU has complete ownership of a given SSD?
Exactly, yes.
So you don't have like any dual port in or anything?
I mean, it's possible to construct such a thing. I think it's not, a fundamental thing. You could not do that. We have chosen to stay with scale-out type of model where, we are relying on these things to be independent failure units. So if a DPU were to fail, there's enough redundancy in other DPUs to pick that function up. So we don't really need to dual port. Right?
The second DPU is really required in order to have 12 additional.
Correct. This is a packaging convenience more than anything. We needed to pick up 2U form factor, right? 24 SSDs fit nicely there. And so the packaging convenience will change over time, right? There's nothing fundamental in this packaging with that regard.
Back to the performance, you've shown that a single DPU can get to about 37 gigabytes, and I'm guessing each one has 400 gigabit ports.
Right. So the question was network connectivity of a DPU. It is, 4 by 100 gig connectivity from each DPU. Yes, go ahead. That's a little bit of a difficult question because each vendor that builds such a thing would have to come out and come up with that answer. And of course, on the CPU compute side also, there's all kinds of different ways of implementing the stack, right? So if you look at stacks that have been around for a while, like Ceph, I think you're looking at hundreds of thousands of IOPS probably, on a Xeon processor. Of course, there's more modern stacks that are using all user mode programming, using pole mode drivers and stuff. I think, they probably get close to 1 million, maybe 2 million, something in that range. Jay may have a better sort of sense of that.
Yeah, and generally I would say between 3 and 8x. I covered some of that in my talk. That's what we see, but it does depend on how deep you
And the difference becomes larger and larger as you increase the number of inline functions, right? So each time you add another inline function, right, the CPU is either not capable of doing that function or it comes at a high premium, either in compute cycles or in memory bandwidth or both. So once you start multiplying all of that, I think the difference could easily become 10 to 20x, or more. Yes, go ahead, please.
So what are your plans with let me rephrase that. So PCI Express, which is the fundamental fabric for NVMe Express, has a clear roadmap going in 64 gigabit transfers a second. We see that bandwidth double. Networking is already evolving. Aren't you putting kind of high-speed paths into everybody's house and then we all go through a good old copper wire?
No, so the ratio of SSDs to DPUs to network, I think it will shift over time, right? As these elements all change, right? So I'm sure there's going to be a leap forward where we go to multiple 100 gig networks. There'll be a leap forward in PCIe. There'll be a leap forward in DPU technology, right? We built only our first generation silicon so far, and there's a lot of improvement we can make into the DPU silicon. So I think all these three elements will grow, and I think what we end up with is how do we repackage this entity so it's well balanced, to your point, right? And then the question also is, do we really need all the lanes? And with Gen 5, right, you need 4 lanes, for example, to an SSD. 2 lanes is enough, and so that also changes the equation. So yeah, there's many things evolving here. So yes. we have to keep adapting our packaging to that. In the back there.
So the data placement is the key in this seems to me. Is that in its own cluster to scalability and avoiding?
Correct. So the question was that data placement is a key, and does it need its own cluster? And yes, as you can see from the graphic here, the composer piece is also a scale-out architecture, right? It's not a single node. And now the question is, how many composer nodes do you need, right? And the scaling of the composer element is really tied to volume scale, your API density, rate of API calls, right? Are you in an environment where you're constantly launching VMs, tearing them down, and your API rate is very high, versus are you in an environment where it's fairly static? So far we see that for a 16-node cluster, 3 nodes are more than sufficient, right? And the other sort of, I would say, expensive, or not expensive, but thing that takes up a lot of resources is telemetry. So with 32 DPUs in your cluster, there's a huge amount of telemetry that's streaming up to the composer, right? I think there was a talk earlier in this track about importance of telemetry. So we are pulling up a huge amount of information from the DPUs. So all of that is being stored and calibrated inside the composer node. So that's another reason you may want to scale the number of composer nodes. So the question is, what is about the protection against composer node failure? So this is where we are relying quite a bit on distributed systems technology. So scale-out databases, there are many out there that provide you that protection. And Kubernetes has a nice protection against monitoring microservices and launching other copies of it. So I think there's a lot of technology available in that area that we can leverage, and we have leveraged at Fungible. So the question is, do the DPUs talk to each other? Yes, they do. As I showed, there are these 3 different types of pipelines, right? So this pipeline that comes from the client and goes out east is actually going to a different DPU. And one example that could happen is that this DPU is hosting a EC4 plus 2 volume, right? So when a write comes in, it has to erasure code and send 5 of those pieces. Run it could store locally, but 5 of those other pieces have to go to other DPUs, right? But the DPU is not making that decision. It's simply being told by the control plane that for this namespace, this is your route table, essentially. This is your arrangement, right? So it's simply following that instruction. It's not making a lot of decisions on how to do that. Please.
This is more related to the customer acceptance kind of the solution. I see the underneath technology you're using is NVMe TCP, right?
The protocol is NVMe TCP.
NVMe TCP.
Right.
And the namespaces, and you talk about ANA and all that thing in there. If you go back to the composer node diagram over there, NVMe TCP as a standard, they're going also into similar kind of a thing with ZNS and all that, putting the more way you write inside the host kind of a thing.
Mm-hmm.
Composer node similar to, does a different functionality than what centralized discovery controller does within NVMe TCP. Different functions, but that's the metadata they're finding. So my question here is twofold. One is that since it's adding value to NVMe transport, are you adding these ideas to NVMe for standardization? So the customers, when they buy the solution, in storage world, everybody has a dual vendor kind of a strategy. They'll have
Right.
AMC this, they'll have HP this kind of thing.
Sure.
And fiber channel works on both of them. So in this case, is the standardization effort, or how you make it a proprietary solution accepted to the customer? That's my question.
So good question. I mean, it's a long question. I'll summarize it as, is this proprietary? And if so, how are we positioning it relative to other standards-based solutions? So the answer is no. It's fully standards-based on the outside of it, right? Inside, of course, we have our own processor. We have our own software implementing this. But to all the hosts in the network, right, this looks like very 100% standards-based, right? So you could not tell that it's a fungible cluster as opposed to a different solution that's also implementing NVMe TCP. And for discovery as well, the composer nodes support NVMe discovery. So for example, from a standard Linux host, there's a command called connect all, right? And so when you do NVMe connect all in Linux, it's going out and talking to a discovery service saying, hey, where are my namespaces? Who is supporting these namespaces? So it's all 100% standards-based. So on both those fronts, you could not tell that this is a fungible storage cluster versus somebody else. Now, the place where it does differ is in the intent API, right? So if somebody has their own orchestration system and says, hey, I want to use your storage cluster, and I know to create volumes and attach them and all that, every vendor's API looks a little bit different there. There are some standards emerging in that area. But also then, that's where I think Cinder and CSI come in. For well-known orchestration systems, again, you could not tell that you're deploying OpenStack and this is a fungible storage cluster running versus somebody else's storage solution that provides a Cinder plugin as well. Right? Yes, please go ahead.
Question. So in one of the other diagrams, you showed the east-west traffic.
Correct.
Right. Is that also standard in TCP, or is that some custom cluster protocol looking to be used?
Right, good question. So the question is the east-west traffic where DPUs are talking to each other, is that also standards-based or a custom protocol? So today in our implementation, it is standards-based. We're using regular NVMe TCP. The DPU does have implementation of what we believe something that's even more scalable and powerful than TCP. But I think that's something we will look to deploy down the road, particularly for east-west. But
Another question. So when the IO comes in, like let's say a write, when does it terminate? Like when do you acknowledge?
good question. So question is, when a write comes into a DPU, when do we acknowledge, right? When does it terminate? So like most implementations, we do rely on non-volatile media, right, to capture the write for several reasons. One is for latency. The second reason is that if you are compressing, right, you cannot just write those very tiny bits. And same thing for erasure coding, right? It's very hard to take a 4 kilobyte write and erasure code it across the network. So we do accumulate writes, and they are all mirrored to other DPUs, right? And then you can select how many redundant paths you want, right? That was sort of the other thing. So when multiple DPUs have acknowledged that, yes, I have this write squirreled away safely in some non-volatile media, that's when we acknowledge the host. We do. We do. We have quite a bit of it working already in the lab, and we do have it in the roadmap, yes. Yes, please go ahead.
Are there any plans for selling DPUs without local storage?
Sure, yes. I think, Fungible is certainly, one line of business for us. Actually, let me repeat the question. Is there a plan to sell DPUs, right, independent of the storage software? Yes, so that is a line of business that the company is interested in. Of course, 5 minutes, guys. So, that, of course, depends a lot on the type of customer that would be able to take a DPU and really develop this type of software, right? Either take our software and modify it or develop their own software. I don't believe that's a big number of such customers out there, but certainly something we are very interested in. Yes?
You mentioned between DPU data path and your composer nodes, at least for data operations. Assume is pretty much nothing. Composer node pushes the map to all DPUs.
Correct.
He knows how to place the data.
Correct. So the top-down, the question was, what is the interaction between composer nodes and the fungible DPUs? So during your normal volume creation attach sequence, it's just instructions going from the composer down to the DPUs, right? Which DPUs are acting as the server for a namespace, right? How data is getting distributed, that map. And then the reverse traffic, of course, is telemetry and error reporting, so event reporting, right? So if an SSD were to fail, the DPU is not going to take any action. It's simply going to report up saying, hey, I lost a SSD. Please send new instructions, right, on what I should do.
Yeah, one more question. The node stuff network, if you have 400 gigabit
Right.
The north-south network, is that the same network that's used for cluster east-west communication?
Correct. Physically, it is. Logically, may or may not be. Right. There are different arrangements we can think of, but today, yeah, it's all one network.
But this will function either way,
It will function either way.
on the same stuff, that same plan, and
Correct.
define what you can isolation separate.
Correct. The question was, is there a separation between the north-south and the east-west network? And the answer is no. Today, it's one unified network. Right? And in fact, really, if you look at this graphic, so is the control part of the network, right? The control instructions are also flowing through that same network. I think probably have time for one last question. I think I saw the 2-minute warning or 5-minute warning. Okay, here you go.
Can you talk a bit about FCP and True Fabric, and why not FCP, why NVMe TCP?
Right. So the question was, can you talk about True Fabric and FCP? So True Fabric is the name of the protocol that we have created in Fungible for essentially, the protocol itself is independent of NVMe. It's really a transport level protocol. And the idea really is, how do we manage end-to-end congestion control? I think one of the issues with TCP is that TCP, for the most part, reacts to congestion in the network. It doesn't prevent congestion in the network. And so question is, for NVMe, can we do better and have something that proactively manages congestion in the network? And that's probably the primary role that FCP provides. And the second thing is that encryption is built into that protocol. So you don't need to run TLS or something. Every packet is encrypted. There are a few other benefits of True Fabric. Now, we do have our implementation running on it. I think we've just chosen to stay with TCP. At least for the initial deployments. I think people are comfortable deploying TCP. Whenever you introduce a new protocol to network administrators, I think they become very nervous, right? So I think this is more, reacting to the market conditions more than technology. We do believe that True Fabric one day, or other forms of it, will come to be. And another reason for that is really, if you fundamentally think about it, NVMe is a datagram-based protocol. It's not a streaming protocol, right? And we have kind of force-fitted, in some ways, a messaging requirement on a streaming protocol, and then you pay for it in terms of head-of-line blocking and other things, right? So question is a reliable datagram, right, in most abstract sense, that has congestion control, the best fit for NVMe transport? And I think the answer is yes, but we have a lot of time, right? We can work on that problem next.
Do you plan this ability for standardization within the transport?
We are interested, yes. We are interested.
Does it require lossless Ethernet, or just
No, it runs on standard. It's really doing end-to-end congestion control. It does require DPUs on both ends, so that's the other thing, right? Yeah, so snapshots are really a property of a namespace, right? So they are fully implemented by the DPU that's serving the namespace, and clones can live anywhere in the cluster. So the clone doesn't have to live in the same DPU as the snapshot. All right, I think we'll call it a day. Thank you so much for those questions. Appreciate it.